order equations, it was homogeneous if the right-hand side was 0, and if there was something else there, it was inhomogeneous. Unfortunately, I've stuck this stuff on the right-hand side, so it's not quite so clear anymore. You have to look for the, it's got to look like that, in other words. So how would the matrix abbreviation look? Well, the left-hand side is x prime. The homogeneous part is ax, just as it's always been. So the only extra part is the r. These two functions are, and I'll write them, since each of this is a column vector. After the multiplication, this is a column vector. What's left is a column vector. Now, explicitly, it's a function of t, given by explicit functions of t, like exponentials, or they could be fancy functions. So that's the thing we're trying to solve. Why don't I put it up in green? Our function. Our new and better and improved system. Well, think back to what we did when we studied inhomogeneous equations, when we were not talking about systems, but just a single equation. What we did was the main theorem, so I guess there are going to be 3 theorems today, not just 2. So theorem C, well, C, okay, C. Is that right? A, B, yes, A, B, we're up to C. Theorem C says, you write it yourself, says that the general solution, that's the general solution to the system, is equal to the complementary function, which is the general solution to x prime equals ax, the homogeneous equation, in other words, plus, what am I going to call it? xp, right you are, a particular solution. But the principle is the same. In other words, and it's proved exactly the same way, it's just linearity and superposition. The linearity of the system, original system, and the superposition principle. So the essence is that to solve this inhomogeneous system, what we have to do is find a particular solution. This part I already know how to do. We've been doing that for 2 weeks. The new thing is to find this. Now, if you remember back before spring break, that most of the work in solving the second order equation was in finding that particular solution. You quickly enough learned how to solve the homogeneous equation, but there was no real general method for finding this. We had an exponential input theorem and with some modifications to it. We took a week's detour in Fourier series to see how to do it for periodic functions or functions defined on finite intervals. There were other techniques which I didn't get around to showing you, techniques involving undetermined method, so-called method of undetermined coefficients, although some of you peeked in your book and learned it from there. But the work is in finding XP. Now, the miracle that occurs here, by contrast, is that it turns out to be easy to find XP. And easy in this further sense that I don't have to restrict the kind of function I use. So that, for example, in the second homework problem I've given you, part 2, the second part 2 homework problem, you'll see how to use systems. For example, to solve this simple equation, I'll write it out for you. Consider that equation. Tangent t. Okay. What technique will you apply to solve that? In other words, suppose you wanted to find a particular solution to that. The right-hand side is not an exponential, it's not a polynomial, it's not like sine or cosine of bt. Could use the Laplace transform. Aha. No, because you don't know how to take the Laplace transform of tangent t. Neither, for that matter, do I. Fourier series, not a good choice for a function which goes to infinity at pi over 2. So you can't do this until you do your homework. Now you'll be able to do it. Okay. So in other words, one of the big things is not only will I give you a formula for the xp, but that formula will work even for tangent t and also any function at all. Okay. Well, I thought I would try to put a little meat on the bones of the inhomogeneous systems by actually giving you a physical problem so we'd actually be able to solve a physical problem instead of just, demonstrate a solution method. So here's a mixing problem. So mixing problem. Just to illustrate what makes a system of equations inhomogeneous. So here are two ugly tanks. Okay, I'm not going to draw these carefully, but they are both 1 liter. Okay? And they're connected by pipes, and I won't bother opening holes in them. So there's a pipe, so fluid's flowing back there, and here, this direction, it's flowing this way. And, but that's not the end. The end is there are stuff coming in to both of them, and I think I'll just make it coming out of this one. There's something realistic. So the numbers 2, 3, 2. Let's start there and see what the others have to be. So these are flow rates. So 1 liter tanks. The flow rates are in, let's say, liters per hour. And I have some dissolved substance in. So here is going to be X salt in there and some same chemical in there, whatever it is. So X is the amount of salt, let's say. Salt in tank 1. And Y, the same thing in tank 2. Now, if you've got stuff flowing unequally this way, you must have balance. Otherwise, you have to make sure that neither tank is getting emptied or bursting and exploding. So what's flowing in? What's X? 3 is going out. 2 is coming in. So this has to be 1 in order that the tank X stay full and not explode. And how about Y? 2 going, 3 coming in. So how much is going out? 2 there and 2 here. 4 is going out. 3 is coming in. So this also has to be 1. Those are just the flow rates of water or the liquid that's coming in. Now, the only thing I'm going to specify is the concentration of what's coming in. So here, the concentration is 5e to the minus t. And that's what makes the problem inhomogeneous. Here, the concentration is going to be 0. In other words, pure water is flowing in here to create the liquid balance. Here, on the other hand, salt solution is flowing in, but with a steadily declining concentration. Okay, so what's the system? What's the system? Well, it's you set it up exactly the way you did it when you studied first order equations. In other words, it's inflow minus outflow. So it's outflow. So it's the out. What's the outflow? The outflow is all in this pipe at 3. So the flow rates are liters per hour. 3 liters per hour flowing out. How much salt does that represent? Well, that times so it's -3 times the concentration of salt. But the concentration, notice, the concentration of X, the concentration equals equals x divided by 1. In other words, x represents both the concentration and the amount. So I don't have to distinguish. If I had made it 2-liter tanks, then I would have had to divide this by 2. So I'm cheating, but it's enough already. Okay. X prime equals minus 3x. That's what's going out. What's coming in? Well, 2y is coming in. Concentration here, what's coming in is at y, 2 liters, plus what's coming in from the outside. So we have to add that in, and that will be plus 5e to the negative t. How about y? Y prime is changing because of what comes in from x, that's 3x. What goes out? Now what goes out? Well, 2 is leaving here, and 2 is leaving here. It doesn't matter that they're going out through separate pipes. They're both going out, so it's minus 4, 2 and 2. How about the inhomogeneous term? Well, there's 1 coming in, but there is no salt in it, and therefore that is not changing. What's coming in through that pipe is necessary for the liquid balance, but it has no effect whatever. I'll put a 0 here, but of course you don't have to put that in. Okay, this is now an inhomogeneous system. So in other words, the system is x prime equals this matrix, negative 3, the same sort of stuff we always had, plus the inhomogeneous term, which is 5, the column vector, 5e to the minus t, and 0. It's the presence of this term that makes the system inhomogeneous, and what that corresponds to is this little closed system being attacked from the outside by these external pipes which are bringing salt in. Without those, of course, the balance would be all wrong. I'd have to change this to 3 and cut that out, I guess. But then it would be just a simple system, homogeneous system. It's these pipes that make it inhomogeneous. Okay, now I should start to solve that, but what I want to do, of course, is, I did this just to illustrate where a system might come from. Before I solve that, what I want to do is, of course, solve it in general. In other words, how do you solve this in general? Because I promised you that you would be able to do in general, regardless of what sort of functions were in the R of T, that column vector. So let's do it. First of all, you have to learn the name of the method. This method is called, so it's a method to or for solving x prime equals ax, and it's a method for finding a particular solution. Of course, to actually solve it, then you have to add the complementary function. So we're looking for a particular solution to this system. Now, the whole cleverness of the method, which I think was discovered a couple of years ago by, I think, Legendre, I'm not sure. The method is called variation of parameters. I'm giving you that so that when you forget it, you'll be able to look it up and be indexed to some advanced engineering mathematics book or something, whatever's on your shelf. But of course, you won't remember the name either, so maybe this won't work. Variation of parameters. I'll explain to you why it's called that. All the cleverness is in the very first line. If you could remember the very first line, then I trust you to do the rest yourself. I don't know any motivation for this first step, but mathematics is supposed to be mysterious anyway. It keeps me eating. So XP, it says, look for a solution, and there will be one of the following form. Now, it will look exactly like... sorry. Look carefully, because it's going to be gone in a moment. It will look there. It will look exactly like this, but of course it can't be this because this solves the homogeneous system. If I plug this in with these as constants, it cannot possibly be a particular solution to this because it will stop there and satisfy that with r equals 0. So the whole trick is you think of these as parameters which are now variable, as constants which are varying. That's why it's called variation parameters. And you think of these, in other words, as functions of t. So we're going to look for a solution which has the form, since they're functions of t, I don't want to call them C1 and C2 anymore. I'll call them V because that's what most people call them. V or U sometimes. The method says, look for a solution of that form. So the variation parameters, these are the parameters that are now varying instead of being constants. Now, if you take it in that form and start trying to substitute it into the equation, you're going to get a mess, and you won't be able. So I think I was wrong in saying I could trust you from this point on. I can only trust you. I'll take the first step from you, and then I can trust you to do the rest after that first step. Okay, the first step is to change the way this looks. Change the way it looks by using the fundamental matrix. Remember what the fundamental matrix was? Its entries were the two columns of solutions. Okay, so these are solutions to the homogeneous equation, the homogeneous system, and I'm going to write it using the fundamental matrix as, now think about it. The fundamental matrix has its columns x1 and x2. Your instinct might be using matrix multiplication to put the V1 and the V2 here, but that won't work. You have to put them here. This says the same thing as that. Let's just take a second out to calculate. So look, the x is going to look like x. I have no notation for this. Oh, yeah, I do. So x1, y1, that's my first solution. My second solution, so here's the fundamental matrix, is x2, y2. And I'm multiplying this on the right by v1, v2. Doesn't it come out right? Look, what's the thing? The top is x1, v1 plus x2, v2. The top, x1, v1 plus x2, v2. It's in the wrong order, but multiplication is commuted, fortunately. And the same way, the bottom thing will be v1, y1 plus v2, y2. v1, y1 plus v2, y2. If I had written it on the other side instead, which is tempting because the v's occur on the left here, that won't work because what will I get? I'll get v1, x1 plus v2, y1, which is not at all what I want. You must put it on the right. But this is a very important thing. This is going to plague us on Monday, too. It must be written on the right and not on the left as a column vector. Okay? So the rest of the program is very simple. Substitute. I'll write it out as a program. Substitute into the system, into that, in other words, and see what V has to be. That's what we're looking for. We know what the x1 and the x2 are. It's the question of what those coefficients are, and see what V is. Let's do it. Okay. Okay, let's substitute. Let's see. So the system is x prime equals ax plus r. So I want to put in xp, this proposed particular solution. That's a fundamental matrix, and the v is unknown. Okay, how do I differentiate the product of two matrices? Look, you differentiate the product of two matrices using the product rule that you learned the first day of 1801. Trust me. Let's do it. So I'm going to substitute in. So in other words, here's my XP, and I'm going to write in what that is. So the left-hand side is the derivative of x prime times v plus x times the derivative of v. Notice that one of these is a column vector and the other is a square matrix. That's perfectly okay. Any two matrices which are the right shape so you can multiply them together, if you want to differentiate their product, in other words, if the entries are functions of t, it's the product rule. Okay. The derivative of this times this plus that times the derivative of this. You've got to keep them in the right order. You're not allowed to shuffle them around carelessly. Okay, so that's that. What's it equal to? Well, the right-hand side is a, and now I substitute just xp in, so that's x times v plus r. So is this progress? So what's v? Looks like a mess. But it's not. Why not? It's because this is not any old matrix X. This is a matrix whose columns are solutions to the system. And what does that do? That means x prime, it satisfies that matrix differential equation. X prime is the same as ax. X prime is the same as ax. And by a little miracle, the v is tagging along in both cases. So this cancels that. And now there is very little left. The conclusion, therefore, is that xv is equal to r. Okay, what's v? It's v that we're looking for, right? It's equal to. Okay, I have to solve a matrix equation now. This is a square matrix, so you have to do it by inverting the matrix, right? You don't just sloppily divide. You multiply on which side by what matrix? Choice of left or right. You multiply by the inverse matrix, on the left or on the right? Has to be on the left. Multiply both sides by x. Oh, I see. Multiply on the right. Yeah, okay. Ambiguous. Okay, multiply both sides of the equation by x inverse on the left, and then you'll get v is equal to x inverse r. Hey, how do I know that x inverse exists? Does x inverse exist? For a matrix inverse to exist, the matrix's determinant must be not 0. Why is this determinant of this not 0? Because its columns are independent solutions. Of course, this is not right. I forgot the prime here. Okay. I'm not failing this course after all. V prime equals that, so this is done by differentiating each entry in the column vector, and therefore we should integrate it. So it'll be the integral, just the ordinary antiderivative of x inverse times r, and this is a column vector. The entries are functions of t. You simply integrate each of those functions in turn. So integrate each entry. And there's my v. And sorry, you can't tell the v's from the r's here. And so finally, the particular solution is xp. xp is equal to, it's really not bad at all. It's equal to x times v. It's equal to x times the integral of x inverse r dt. Now, actually, there isn't much work to doing that. Once you've got solved the homogeneous system and gotten the fundamental matrix, taking the inverse of a 2x2 matrix is almost trivial. You flip those two and you change the signs of these two and you divide by the determinant and multiply it by r. And the hard part is if you can do the integration. If not, you just leave it the integral sign the way you've learned to do in this silly course. And you you've still got the answer. So what about the arbitrary constant of integration? The answer is you don't need to put it in. Just find one particular solution is good enough. You don't have to put in the arbitrary constants of integration because they are already in the complementary function here. And therefore you don't have to add them. I'm sorry I didn't get a chance to actually solve that. I'll have to let it go. The recitations will do it on Tuesday. We'll solve that particular problem, which means you will, in effect. We're going to need a few facts about fundamental matrices, and I'm worried that over the weekend, this spring activities weekend, you might have forgotten them. So I'll just spend 2 or 3 minutes reviewing the most essential things that we're going to need later in the period. So what we're talking about is, I'll try to color code things so you'll know what they are. First of all, the basic problem is to solve a system of equations, and I'm going to make that a 2-by-2 system, although practically everything I say today will also work for n-by-n systems. Your book tries to do it n-by-n as usual, but I think it's easier to learn 2-by-2 first and generalize rather than to wade through the complications of n-by-n systems. So the problem is to solve it, and the method I used last time was to describe something called a fundamental matrix. A fundamental matrix for the system or for A, whichever you want. Remember what that was? That was something it was a 2-by-2 matrix of functions of t, and whose columns were 2 independent solutions. x1, x2, these were 2 independent solutions. In other words, neither was a constant multiple of the other. Now, I spent a fair amount of time showing you the 2 essential properties that a fundamental matrix had. So we're going to need those today. So let me remind you the basic properties. The basic properties of X and the properties by which you could recognize one, if you were given one, is first of all the easy one, that its determinant shall not be 0. It is not 0 for any t, for any value of the variable. That simply expresses the fact that its 2 columns are independent, linearly independent, not a multiple of each other. The other one was more bizarre, so I tried to call a little more attention to it. It was that the matrix satisfies a differential equation of its own, which looks almost the same, except it's a matrix differential equation. It's not column vectors which are solutions, but matrices as a whole which are solutions. In other words, X, if you take that matrix and differentiate every entry, what you get is the same as A multiplied by that matrix you started with. This, remember, expressed the fact, it was just really formal when you analyze what it was, but it expresses the fact that the columns, it says that the columns solve the system. So the first thing says the columns are independent, and the second say that the columns, each column separately, is a solution to the system. That's as far as more or less. Then I went in another direction. We talked about variation of parameters. I'm not going to come back to variation of parameters today. We're going in a different tack. The tack we're going on is I want to first talk a little more about the fundamental matrix, and then, as I said, we'll talk about an entirely different method of solving the system, one which makes no mention of eigenvalues or eigenvectors, if you can believe that. But first, the one confusing thing about the fundamental matrix is that it is not unique. I've been carefully trying to avoid talking about the fundamental matrix because there is no the fundamental matrix. There is only a fundamental matrix. Why is that? Well, because these two columns can be any two independent solutions, and there are an infinity of ways of picking independent solutions. That means there are an infinity of ways, infinity of possible fundamental matrices. Well, that's disgusting, but can we repair it a little bit? I mean, maybe they're all derivable from each other in some simple way, and that's, of course, what is true. Now, as a prelude to doing that, I'd like to show you what I should have showed you on Friday, but again, I ran out of time. How do you write the general solution to the system? The system I'm talking about is that pink system. Well, of course, the standard naive way of doing it is it's x equals, the general solution is an arbitrary constant times that first solution you found, plus C2 times the second, another arbitrary constant times the second solution you found. Okay, now how would you abbreviate that using the fundamental matrix? Well, I did something very similar to this on Friday, except these were called V's. It was part of the variation of parameters method, but I promised not to use those words today, so I just said nothing. Okay, what is the answer? So it is x equals, how do I write this using the fundamental matrix, x1, x2? Simple.
Okay, yeah.
It's capital X times the vector whose columns, the vector whose entry, column vector whose entries are C1 and C2. In other words, it is x1, x2 times the column vector C1, C2. Isn't it? Yeah, because if you multiply this, think top row, C1, top row plus top row times C2. That exactly gives you the top row here. And the same way the bottom row here times this vector gives you the bottom row of that. So it's just another way of writing that, but it looks very efficient. Now, sometimes efficiency isn't a good thing. You have to watch out for it. But here it's good. So this is the general solution, written out using a fundamental matrix, and you can't use less symbols than that. There's just no way. Well, but that gives us our answer to what do all fundamental matrices look like. Well, their two columns are solutions. So the answer is they look like X. Now, the first column is an arbitrary solution. How do I write an arbitrary solution? Okay. There's the general solution. I make it a particular one by giving a particular value to that column vector of arbitrary constants, like 2, 3, or minus 1 pi, or something like that. So, if the first guy is a solution, and I've just shown you I can write such a solution like x C1 with a column vector, a particular column vector of numbers. This is a solution because the green thing says it is. And side by side, we'll write another one. And now all I have to do is, of course, they're supposed to be independent. We'll worry about that in just a moment. All I have to do is make this look better. Now, I showed you last time, by the laws of matrix multiplication, if the first column is xc1 and the second column is xc2, using matrix multiplication, that's the same as writing it this way. This square matrix times the matrix whose entries are the first column vector and the second column vector. Now, I'm going to call this C. It's a square matrix of constants. It's a 2 by 2 matrix of constants. And so the final way of writing it is x times, it's just what corresponds to that, but x times C. Ooh. And so this is the most general so x is a given fundamental matrix, this one, that one. So the most general fundamental matrix is then the one you started with and multiply it by an arbitrary square matrix of constants, except you want to be sure that the determinant is not 0. Well, the determinant of this guy won't be 0, so all you have to do is make sure that the determinant of C isn't 0 either. So in other words, the fundamental matrix isn't unique, but once you've found one, all the other ones are found by multiplying it on the right by an arbitrary square matrix of constants, which is non-singular, has determinant not 0, in other words. Well, that was all Friday. That's Friday leaking over into Monday. And now we begin the true Monday. So here's the problem. Once again, we've got we've got our 2x2 system, or n by n if you want to be super general. There's our system. What have we got so far by way of solving it? Well, somebody, your kid brother or sister, when you go home, says, okay, precocious kid, says, okay, so tell me how to solve this thing. I think the only thing you'll be able to say, well, you do this, you take the matrix, and then you calculate something called eigenvalues and eigenvectors. You know what those are? Yeah, I didn't think you did, blah, 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 well, how smart I am. And you then explain what the eigenvalues and eigenvectors are, and then you show how to, of those, make up special solutions, and then you take a combination of that. And in other words, it's an algorithm. It's something you do, a process, a method. And when it's all done, you have the general solution. Now, that's fine for calculating particular problems, with definite numbers, a definite model with definite numbers in it where you want a definite answer. And, of course, a lot of your work in engineering and science classes is that kind of work. But the further you get on, well, when you start reading books, for example, or, God forbid, start reading papers in which, people are telling you, they're doing engineering or they're doing science. They don't want a method. What they want is a formula. In other words, the problem is to fill in the blank in the following. You're writing a paper, and you just set up some elaborate model, and A is a matrix derived from that model in some way, represents bacteria doing something or bank accounts doing something, I don't know. And you say, as is well known, the solution is, of course, you've only got letters here.
Okay.
No numbers. This is a general paper. The solution is given by the formula The only trouble is we don't have a formula. All we have is a method. Now, people don't like that. So what I'm going to produce for you this period is a formula. And that formula does not require the calculation of any eigenvalues, eigenvectors, doesn't require any of that. It's therefore a very popular way to finish that sentence. Now the question is, where's that formula going to come from? Well, we are, for the moment, clueless. If you're clueless, the place to look always is, do I know anything about this sort of thing? I mean, is there some special case I could solve of this problem I could solve, or that I have solved in the past? And the answer to that is yes. You haven't solved it for a 2x2 matrix, but you have solved it for a 1x1 matrix. A 1x1 matrix also goes by the name of a constant. It's just a thing. It's a number. Just putting brackets around it doesn't conceal the fact that it's just a number. So let's look at what's the solution for a 1x1 matrix. The 1x1 case. If we're looking for a general solution for the n by n case, it must work for the 1x1 case also. That's a good motivation, a good reason for us starting. That looks like X, doesn't it? X inside. One boy, one case. Well, in that case, I'm trying to solve the system. The system consists of a single equation. That's the way the system looks. How do you solve that? Well, you were born knowing how to solve that, or you, anyway, certainly didn't learn it in this course. Solution is, well, you separate variables, blah, 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 blah. And the solution is x equals, the basic solution is e to the at, and you multiply that by an arbitrary constant. Now, if that's a formula, it's a formula for the solution. And it uses the parameter in the equation. I didn't have to know a special number. I didn't have to put a particular number here to use that. Well, the answer is that the same idea, whatever the answer I give here, has got to work in this case too. So I'll just, let's take a quick look as to why this works. Of course, you know, you separate variables and use calculus. I'm going to give you a slightly different argument, which has the advantage of generalizing to the end of the case. And the argument goes as follows for that. It uses the definition of the exponential function not as the inverse to the logarithm, which is where the fancy calculus books get it from, nor as the naive high school method, you know, it's e squared means you multiply e by itself, and e cubed means you do it 3 times, and so on, and e to the 1/2 means you do it a half a time or something. So the naive definition of the exponential function, instead I'll use the definition of the exponential function that comes from an infinite series. So leaving out the arbitrary constant, which we don't have to bother with, e to the at is the series 1 plus at plus a squared t squared over 2 factorial. I'll put out one more term and let's call it quits there. If I take this, and then the argument goes, let's just differentiate it. In other words, what's the derivative of e to the at? With respect to t, well, just differentiating term by term, it's 0 plus the first term is a, the next term is a squared times t. This differentiates to t squared over 2 factorial. And the answer is that this is equal to a times, if you factor out the a, what's left is 1 plus at plus a squared t squared over 2 factorial. In other words, it's simply a e to the at. In other words, by differentiating the series, using the series definition of the exponential, and by differentiating it term by term, I can immediately see that it satisfies this differential equation. What about the arbitrary constant? Well, if you like, you can include it here, but it's easier to observe that by linearity, if e to the at solves the equation, so does the constant times it, because it's linear. The equation is linear. Now, that's the idea that I'm going to use to solve the system in general. What are we going to say? Well, what could we say? Solution 2. The solution to, well, it's better, let's get 2 solutions at once by writing a fundamental matrix. So, a fundamental matrix, I don't claim it's the one, a fundamental matrix for the system x prime equals ax. So that's what we're trying to solve. And we're going to get 2 solutions by getting a fundamental matrix for it. And the answer is e to the at. Isn't that what it should be? That little guy had a little a. Now we've got a matrix. Okay, just put the matrix up there. Now, what on earth is first person who must have thought of this, it happened about 100 years ago. You know, what meaning should be given to e to a matrix power? Well, clearly the two naive definitions won't work. The only possible meaning you could try for is using the infinite series, but that does work. So this is a definition I'm giving of the exponential matrix. It is. Now notice the A is a 2 by 2 matrix, multiplying it by T. What I have up here is basically a 2 by 2 matrix. Its entries involve T, but it's a 2 by 2 matrix. Okay, it's going to be. Leave out, so we're trying to get the analog of that formula over there. Well, it's going to be. Leave the first term out just for the moment. The next term is going to surely be A times T. This is a 2 by 2 matrix, right? What should the next term be? Well, A squared times T squared over 2 factorial. What kind of a guy is that? Well, if A is a 2 by 2 matrix, so is A squared. How about this? This is just a scalar which multiplies every entry of A squared. And therefore, this is still a 2 by 2 matrix. That's a 2 by 2 matrix. This is a 2 by 2 matrix. No matter how many times you multiply A by itself, it stays a 2 by 2 matrix. It gets more and more complicated looking, but it's always a 2 by 2 matrix. And now I'm multiplying every entry of that by T cubed, the scalar T cubed over 3 factorial. And continuing on in that way, what I get, therefore, is a sum of 2 by 2 matrices. Well, you can add 2 by 2 matrices to each other. We've never made an infinite series of them, but in fact, we haven't done it, but others have. And this is what they wrote. The only question is, what should we put at the beginning? Over there, I have 1, the number 1, but I, of course, cannot add the number 1 to 2 by 2 matrices. What goes here must be a 2 by 2 matrix, which is the closest thing to 1 I can think of. What should it be? The I. 2 by 2 I. The 2 by 2 identity matrix. Looks like the natural candidate for what to put there. And in fact, it's the right thing to put there. Okay, now I have a conjecture. You know, purely formally, changing all with a keystroke of the computer, all the little a's have been changed to capital A's, and now all I have to do is wonder if is this going to work. Well, what's the basic thing I have to check to see that it's a fundamental matrix? So the question is this, I wrote it down all right, but is this a fundamental matrix for the system? Well, I have a way of recognizing a fundamental matrix when I see one. The critical thing is that it should satisfy this matrix differential equation. So that's what I should verify. Does this guy that I've written down satisfy that equation? And the answer is, it satisfies. So number 2 is, it satisfies x prime equals ax. In other words, plugging in x equals this e to the at, whose definition I just gave you. If I substitute that in, does it satisfy that matrix differential equation? And the answer is yes. I'm not going to calculate it out because the calculation is absolutely identical to what I did there. The only difference is when I differentiated it term by term. How do you differentiate something like this? Well, you differentiate every term in it, but if you work it out, it's simply, this is a constant matrix, every term of which is multiplied by t squared over 2 factorial. Well, if you differentiate every term, every entry of that constant, of that matrix, what you're going to get is a squared times just the derivative of that part, which is simply t. And the same way. In other words, the formal calculations looks absolutely identical to that. So the answer to this is yes. By the same calculation as before. As for the 1 by 1 case. And now the only other thing to check is that the determinant is not 0. In fact, the determinant is not 0 at one point. That's all you have to check. What's x of 0? What's the determinant at the value of the determinant of x is e to the at? What's the value of of this thing at 0? Here's my function. If I plug in t equals 0, what's it equal to? I. What's the determinant of I? 1. It is certainly not 0. So by writing down this infinite series, I've got my two solutions. Its columns give me two solutions to the original system. There were no eigenvalues, no eigenvectors. I have a formula for the answer. What's the formula? It's e to the at. And of course, anybody reading the paper is supposed to know what e to the at is. It means that. This is just marvelous. There must be a fly in the ointment somewhere. Only a teeny little fly. The teeny little fly, and it's almost impossible to calculate that series for all reasonable times. However, once in a while it is. So let me give you an example where it is possible to calculate the series and where you get a nice answer. So let's work out an example. By the way, I should, nowadays, we're not back 50 years. The exponential matrix has the same status on, say, a MATLAB or Maple or Mathematica as the ordinary exponential function does. It's just a command you type in. You type in your matrix, and you now say exp of that matrix, and out comes the answer to as many decimal places as you want. It'll be a square matrix with entries, carefully written out. So in that sense, the fact that we can't calculate it shouldn't bother us. There are machines to do the calculations. What we're interested in is it as a theoretical tool. But let's, in order to get any feeling for this at all, we certainly have to do a few calculations. So let's do an easy one. Let's consider the system x prime equals y, y prime equals x. This is very easily done by elimination, but that's forbidden. So first of all, we write it as a matrix. So x prime, it's the system x prime equals 0, 1, 1, 0, x. So here's my A. And so e to the at is going to be, so A is 0, 1, 1, 0. So what we want to calculate is we're going to get both solutions at once by calculating at one fell swoop e to the at. Okay, e to the at equals. Okay, I'm going to actually write out these guys. Well, obviously the hard part, and the part which is normally going to prevent us from calculating this series explicitly, by hand anyway, as I say, the computer can always do it, is the value. How do we raise a matrix to a high power? You just keep multiplying and multiplying and multiplying. That looks like a rather forbidding and unpromising activity. Well, here it's easy. Let's see what happens. What is A? If that's A, what's A squared? I'm going to have to calculate that as part of the series. So that's going to be 0, 1, 1, 0 times 0, 1, 1, 0, which is, da-da. So, 1, 0, 0, 0, 1 plus 0. We are saved. It is the identity. Now, from this point on, we don't have to do any more calculations, but I'll do them anyway, what's A cubed? Don't start from scratch again. God, from 1 times 1, no. A cubed is A squared times A, and A squared is in real life the identity. Of course, you would do all this in your head, but I'm being a good boy writing it all out. So this is I, the identity, times A, which is A. I'll do one more. What's A to the fourth? Now, you would be tempted to say A to the fourth is A squared, which is I times I, which is I, but that would be wrong. A to the fourth is A cubed times A, which is A cubed, I've just calculated is A times A. A cubed I just calculated was A, right? And now that is A squared, which is the identity. It's clear this is, by this argument, it's going to continue in the same way. Each time you add an A on the right-hand side, you're going to keep alternating between the identity A, the next one will be the identity, the next will be A. So the end result is that the first term of the series is simply the identity. The next term of the series is A, but it's multiplied by T. So that is 0. Should I put it? I'll keep the T on the outside. Remember, when you multiply a matrix by a scalar, that means multiply every entry by that scalar. So this is the matrix 0, T, T, 0. I'll do a couple more terms. The next term would be, well, A squared we just calculated is the identity. So that looks like this, except now I multiply every term by T squared over 2 factorial. All right, go for broke. The next one will be this, times T cubed over 3 factorial. And fortunately, I've run out of room. Okay, let's calculate then. Maybe I should do it. Well, no, we're going to need that. Okay, let's do it here. So what's the final answer for e to the AT? It is, I have an infinite series of 2 by 2 matrices. Let's look at the term in the upper left-hand corner. It's 1 plus 0 times T plus 1 times T squared over 2 factorial plus 0 times T. It's going to, in other words, be 1 plus T squared over 2 factorial plus the next term. It's not on the board, but I think you can see it's this. And it continues on in the same way. How about the lower left term? Well, that's 0 plus T plus 0 plus T cubed over 3 factorial and so on. So it's T plus T cubed over 3 factorial plus T to the 5th over 5 factorial. The other terms in the other two corners are just the same as these. This one, for example, is 0 plus T plus 0 plus T cubed over 3 factorial. And the lower one is 1 plus 0 plus T squared, and so on. So it's it's the same as 1 plus T squared over 2 factorial, and so on. And up here we have T plus T cubed over 3 factorial, and so on. Well, that matrix doesn't look very square, but it is. It's infinitely log physically, but it isn't. It's got one term here, one term here, one term here, one term there. Now, all we have to do is make those terms look a little better. For here, I have to rely on the culture which you may or may not possess. You would know what these series were if only they alternated their signs. If this were a negative, 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 then the top would be cosine t, and this would be sine t. But they don't. So they are the next best thing. They are hyperbolics. Right? The top is not cosine t, but cosh t. The bottom is sig t. And how do we know this? Because you remember. And what if I don't remember? You know now. That's why you come to class. Well, for those of you who don't, and in fact, remember the nice way to, so this is e to the t plus e to the negative t. It should be over 2, but I don't have room to put in the 2. This doesn't mean I will omit it. It just means I will put it in at the end by multiplying every entry of the matrix by 1/2. So if you've forgotten what cosh t is, it's e to the t plus e to the negative t divided by 2, and the similar thing for sig t. So there is your first explicit exponential matrix calculated according to the definition. And what we have found is the solution to the system, x prime equals y, y prime equals x. A fundamental matrix, in other words, are cosh t and sinh t satisfy both of those, are both solutions to that system. Now, there's one thing people love the exponential matrix in particular for, and that is the ease with which it solves the initial value problem. It's exactly what happens in studying the single system, the single equation, x prime equals ax. But let's do it in general. What's the initial value problem? Well, the initial value problem is we start with our old system, but now I want to plug in initial conditions. I want the particular solution which satisfies the initial condition. Let's make it at 0 to avoid complications, to avoid a lot of notation. This is to be some starting value. So this is a certain constant vector. It's to be the value of the solution at 0. And the problem is find what x of t is. Well, if you're using the exponential matrix, it's a joke. It's a joke. Shall I derive it or just do it? All right. The general solution, let's derive it, and then I'll put up the final formula in a box so that you'll know it's important. What's the general solution? Well, I did that for you at the beginning of the period. Once you have a fundamental matrix, you get the general solution by multiplying it on the right by an arbitrary constant vector. So the general solution is going to be x equals e to the at. That's my super fundamental matrix, found without eigenvalues and eigenvectors. And this should be multiplied by some unknown constant vector, c. So the only question is, what should the constant vector c be? So we'll plug in, to find c, I'll plug in 0. When t is 0, here I get x of 0. Here I get e to the a times 0 times c. Now what's this? This is the vector of initial conditions. What's e to the a times 0? E to the a times 0. Plug in t equals 0. What do you get? I. Therefore, c is what? C is x0. It's a total joke. It's a total joke, and the solution is, to the initial value problem, is x equals e to the at times x0. It's just what it would have been in one variable. The only difference is that here we're allowed to put the c out front. In other words, if I asked you to put in the initial condition, you'd probably write x equals little x0 times e to the at. And you would be tempted to do the same thing here. X equals vector x0 times e to the at. Now, you can't do that, and if you try to, MATLAB will hiccup and say, illegal operation. What's the illegal operation? Well, x is a column vector from the system. It's a column vector. That means the initial conditions are also a column vector. You cannot multiply a column vector out front and the square matrix afterwards. You can't. If you want to multiply a matrix by a column vector, it has to come afterwards, so you can do zing, zing. There is no zing. You see, there is no. You can't put it in front. It doesn't work. So it must go behind. That's the only place you might get tripped up. And as I say, if you try to type that in using MATLAB, you will immediately get error messages that it's illegal. Can't do that. So anyway, we've got our solution. So there's our system. It's our initial value problem anyway is in pink, and its solution using the exponential matrix is in green. Now, the only problem is we still have to talk a little bit more about calculating this. Now, the principal warning with an exponential matrix is that once you've gotten by the simplest things involving it, the fact that it solves systems, gives you the fundamental matrix for a system, then you start flexing your muscles and say, oh, well, let's see what else we can do with this. For example, the reason exponentials came into being in the first place was because of the exponential law, right? I'll kill anybody who sends me emails saying, hey, what's the exponential law? Okay, the exponential law would say that e to the a plus b is equal to e to the a times e to the b. The law of exponents, in other words. It's the thing which makes the exponential function different from all other functions. That it satisfies something like that. Now, first of all, does this make sense? That is, are the symbols compatible? Let's see. This is a 2 by 2 matrix. This is a 2 by 2 matrix, so it does make sense to multiply them, and the answer will be a 2 by 2 matrix. How about here? This is a 2 by 2 matrix. Add this to it, it's still a 2 by 2 matrix. E to a 2 by 2 matrix still comes out to be a 2 by 2 matrix. So both sides are legitimate 2 by 2 matrices. The only question is, are they equal? And the answer is, not in a pig's eye. How could this be? Well, I didn't make up these laws. I just obey them. I wish I had time to do a little calculation to show you that it's not true. But it is true in a certain special cases. It's true in the special case. And this is pretty much if and only if statement. The only case in which it's true is if A and B are not arbitrary square matrices but commute with each other. You see, if you start writing out the series to try to check whether that law is true, you'll get a bunch of terms here, a bunch of terms here, and you'll find that those terms are pairwise equal only if you're allowed to let the matrices commute with each other. In other words, if you can turn AB plus BA into twice AB, then everything will work fine. But if you can't do that, it will not. Now, when do two square matrices commute with each other? The answer is almost never. It's just a lucky accident if they do. But there are 3 cases of the lucky accident which you should know. So the 3 cases, I feel justified in calling it the 3 cases. The 3, oh well, I don't know, maybe I shouldn't do that. So the 3 most significant examples are, example number 1, when A is a constant times the identity matrix. In other words, when A is a matrix which looks like this. That matrix commutes with every other square matrix. If that's A, then this law ABB is always true, and you're allowed to use this. Okay, so that's one case. Another case, when A is more general, is when B is equal to negative A. I think you can see that that's going to work, because A times minus A is equal to minus A times A. Yeah, they're both equal to A squared, except with a negative sign in front. And the third case is when B is equal to the inverse of A. Because AA inverse is the same as A inverse A, they're both the identity. Of course, A must have an inverse. Okay, let's suppose it does. Now, of them, this is I think the most important one, because it leads to this law, which is the form in which you shouldn't. That's forbidden, but there's one case of it which is forbidden, which is not forbidden, and that's here. What will it say? Well, that will say that e to the A minus A is equal to e to the A times e to the negative A. So this is true, even though the general law is false. It's because A and negative A commute with each other. But now what does this say? What's e to the 0 matrix? In other words, suppose I take the matrix that's 0 and plug it into the formula for E. What do you get? E to the 0 times t is I. It has to be a 2 by 2 matrix if it's going to be anything. It's the matrix I. So this side is I. This side is the exponential matrix. And what does that show? It shows that the inverse matrix to e to the a is e to the negative a. That's a very useful fact. That the inverse to, this is the main survivor of the exponential law. In general, it's false, but this standard corollary of the exponential law is true, is equal to e to the minus a. Just what you would dream and hope would be true. Okay, I've got exactly 2.5 minutes left, which to do the impossible. All right. The question is, how do you, to calculate e to the at, you can use series, but rarely works. It's too hard. You know, there are a few examples, and you'll have some more for homework, but in general it's too hard because it's too hard to calculate the powers of a general matrix A. There's another method which is useful only for matrices which are symmetric, but like that, well, it's more than symmetric. These two have to be the same, but you can handle those, as you'll see from the homework problems, by breaking it up this way and using the exponential law. So this would be 0, B, B, 0. See, these two matrices commute with each other, and therefore I can use the exponential law. This leaves all other cases. And here's the way to handle all other cases. All other cases. In other words, if you can't calculate the series and this trick doesn't work, are done as follows. You start with an arbitrary fundamental matrix, not the exponential matrix. You multiply it by its value at 0. That's a constant matrix, and you take the inverse of that constant matrix. It will have one because, remember, the fundamental matrix never has determinant 0, so you can always take its inverse for any value of t. Now, what property does this have? It's a fundamental matrix. How do I know that? Well, because I found all fundamental matrices for you. Take any one, multiply it by a square matrix on the right-hand side, and you get still a fundamental matrix. And what's its value at 0? Well, it is x of 0 times x of 0 inverse. So its value at 0 is the identity. Now, e to the at has these same two properties. Namely, it's a fundamental matrix, and its value at 0 is the identity. Conclusion, this is e to the at. In other words, and that's the garden variety method of calculating the exponential matrix. If you want to give it explicitly, start with any fundamental matrix calculated, you should forgive the expression, using eigenvalues and eigenvectors and putting the solutions into the columns. Evaluate it at 0, take its inverse, multiply the two, and what you end up with has to be the same as the thing calculated with that infinite series. Okay, you'll get lots of practice for homework, and tomorrow. Everything I say today is going to be for n-by-n systems, but for your calculations in the exams, 2 by 2 will be good enough.
So our system looks like that. Notice I'm talking today about the homogeneous system, not the inhomogeneous system. So homogeneous. And we have so far two basic methods of solving it. The first one, on which we spent the most time, is the method of where you calculate the eigenvalues of the matrix, the eigenvectors, and put them together to make the general solution. So eigenvalues, e-vectors, and so on. The second method, which I gave you last time, I call the Royal Road, simply calculates the matrix e to the at and says that the solution is e to the at times x0, the initial condition. That's very elegant. The only problem is that to calculate the matrix e to the at, although sometimes you can do it by its definition as an infinite series, most of the time the only way to calculate the matrix e to the at is by using the fundamental matrix. In other words, the normal way of doing it is you have to calculate it as the fundamental matrix time normalized at 0. So, as I explained at the end of last time, and you've practiced in the recitations, you have to find the fundamental matrix, which of course you have to do by eigenvalues and eigenvectors, and then you multiply it by its value at 0 inverse. And that, by magic, turns out to be the same as the exponential matrix. But of course, there has been no gain in simplicity or no gain in ease of calculation. The only difference is that the language has been changed. Now, today is going to be devoted to yet another method which saves no work at all, and it only amounts to a change of language. The only reason I give it to you is because I've been begged by various engineering departments to do so, because that is the language they use. In other words, each person who solves systems, some like to use fundamental matrices, some just calculate, some immediately convert the system by elimination into a single higher order equation because they're more comfortable with that. Some talk, especially if they're writing papers, they talk exponential matrices. But there are a certain number of engineers and scientists who talk decoupling. Express the problem and the answer in terms of decoupling, and that's therefore what I have to explain to you today. So the third method, today's method, I stress it's no more than a change, really no more than a change of language, and I feel a little guilty about the whole business because it's, instead of going more deeply into studying these equations, what I'm doing is it's like giving a language course, and I'm teaching you how to say hello and goodbye in French, German, Spanish, Italian. It's not going very deeply into any of those languages, but you're going into the outside world where people will speak these things. So here's an introduction to the language of decoupling, in which some people is the exclusive language in which they talk about systems. Now, I think the best way to, in a general way, what you try to do is as follows. You try to introduce new variables. You make a change of variables. I'm going to do it just 2 by 2, just to save a lot of writing out. And so let's call the change. It's going to be a linear change of variables because we're interested in linear systems. So the problem is to find u and v such that something wonderful happens, such that when you make the change of variables to express this system in terms of u and v, it becomes decoupled. And that means the system turns into a system which looks like u prime equals k1 times u and v prime equals k2 times v. Such a system is called decoupled. Why? Well, a normal system is called coupled. Let's write it out what it would be. It would look like, I can't use let's not write it out. You know what it looks like.
This is decoupled because it's not really a system at all. It's just two first-order equations sitting side by side and having nothing whatever to do with each other. This is two problems from the first day of the term. It is not one problem from the next to last day of the term, in other words. To solve this, all you say is u is equal to a constant, some constant times e to the k1t, and v equals another constant times e to the k2t. Coupled means that the x and y occur in both equations on the right-hand side, and therefore you cannot solve separately for x and y. You must solve together for both of them. Here I can solve separately for u and v, and therefore the system has been decoupled. Now, obviously, if you can do that, it's an enormous advantage, not just in the ease of solution, because you can write down the solution immediately, but because something physical must be going on there. There must be some insight. There ought to be some physical reason for these new variables. Now, that's where I plan to start with. So my plan for the lecture is, first, to work out in some detail a specific example where the decoupling is done, to show how that leads to the solution, and then we'll go back and see how to do it in general, because you will see that as I do the decoupling in this particular example, that particular method, though it's suggestive, it will not work in general. I need a more general method. But let's first go to the example. It's a slight modification of one you should have done in recitation. I don't think I worked one of these in the lecture, but to describe it, I have to draw two views of it to make sure you know exactly what I'm talking about. So it's our old, sometimes it's called an ice cube, the two-compartment ice cube tray problem. You know, you fill an ice cube. It's a very old-fashioned type of ice cube tray, not a modern one, which is all plastic and where there's no leaking from one compartment to another. But the old kind of ice cube tray, you know, there were compartments and these were metal separators, and you leveled the liquid because it could leak through the bottom. They didn't go right to the bottom. If you don't know what I'm talking about, it makes no difference. So I'm going to so this is the side view. This is meant to be twice as long, but to make it quite clear, I'll draw the top view of this thing. You have to imagine this is a rectangle, all the sides are parallel and everything. This is 1 and this is 2. All I'm trying to say is that the cross-sectional area of these two chambers, this one has twice the cross-sectional area of this one. So I'll write a 2 here and I'll write a 1 there. Of course, it's this hole here through which everything leaks. I'm going to let x be the height of this liquid, the water here, and y the height of the water in that chamber. Obviously, as time goes by, they both reach the same height because of somebody's law. Now, what's the system of differential equations which controls this? Well, the essential thing is the flow rate through here. So that flow rate through the hole in units, let's say in liters per second, so you understand, I'm talking about the volume of liquid that goes through. I'm not talking about the velocity. That's proportional to the area of the hole, the cross section, the size of the hole. So the area of the hole, the cross-sectional area, right? And it's also times the velocity of the flow. But the velocity of the flow depends upon the pressure difference. And that pressure difference depends upon the difference in heights. All those are various people's laws. So times the height difference. And of course you have to get the sign right. So I just pointed out the height difference is proportional to the pressure at the hole. And it's that pressure at the hole which determines the velocity with which the fluid flows through. So where does this all produce our equations? Well, x prime is equal to, therefore, some constant depending on the area of the hole and this constant of proportionality with the pressure and the units and everything else, times the pressure difference I'm talking about. Well, if fluid is going to flow in this direction, that must mean the height, the y height is higher than the x height. So it should be, to make x prime positive, it should be y minus x here. Now, the y prime is different because, again, the rate of fluid flow is determined. This time it will be x minus, if y prime is positive, if this is rising as it will be in this case, it's because the fluid is flowing in that direction. It's because x is higher than y. So this should be the same constant, x minus y. But notice that that will not, that's the rate at which the right-hand side is the rate at which fluid is flowing into this tank. That is not the rate at which y is changing. It's the rate at which 2y is changing. Why isn't there a constant here? There is, it's 1. That's the one that's this one cross-section. So the area here is 1, and the area, cross-sectional area here is 2. And that's the reason for the 1 here and the 2 here. Because we're interested in the amount by which the fluid is, the rate at which fluid is being added to this, which is only related to the height, the rate at which the height is rising, if you take into account the cross-sectional area. So there's the system. In order to make, use nothing but integers here, I'm going to take c equal to 2 so I don't have to put in halves. So the final system is x prime equals minus 2x, you got to write them in the right order, right? And y prime equals, the 2's cancel because c is 2, so now it's x minus y. So there's our system, and now the problem is I want to solve it by decoupling it. I want, in other words, to find new variables, u and v, which are better, more natural to the problem than the x and y, that are so natural to the problem that the system, the new system, will just consist of the two side-by-side equations instead of the single equation. So the question is, what should u and v be? Now, the difference between what I'm going to do now and what I'm going to do later in the period is, later in the period, I'll give you a systematic way of finding what u and v should be. Now, we're going to psych out what they should be, in the way in which people who solve systems often do. I'm going to use the fact this is not just an abstract system of equations, it comes from some physical problem, and I ask, is there some system of variables which somehow go more deeply into the structure of this, what's going on here, than the naive variables which simply tell me how high the two tank levels are? That's the obvious thing I can see, but are there some variables which go more deeply? Now, one of them is obvious, sort of obvious, and suggested both by the form of the equation and by this. It's simply the difference in heights is in some ways a more natural variable because that's directly related to the pressure difference, which is directly related to the velocity of flow. They will differ by just constant. So I'm going to call that the second variable, the difference in heights, let's call it. So that's x minus y. That's a very natural variable for the problem. The question is, what should the other one be? Now you sort of stare at that a while until it occurs to you that something is constant. What's constant in this problem? Well, the tank is sitting there, that's constant. But what thing which might be a variable is clearly a constant, must be a constant? It would be the total amount of water in the two tanks. These things vary, but the total amount of water stays the same because it's a homogeneous problem. No water is coming in from the outside and none is leaving the tanks through a little hole. Okay, what's the expression for the total amount of water in the tanks? X plus 2y. Therefore, that's a natural variable also. It's independent of this one. It's not a simple multiple of it. It's a really different variable. So this represents the total amount of, this variable represents the total amount of water, of liquid in the two tanks. This represents the pressure up to a constant factor. It's proportional to the pressure at the hole. Okay, now what I'm going to do is say, okay, this is my change of variables, and now let's plug in and see if what happens to the system when I plug in these two variables. Now, how do I do that? Well, so I want to substitute, get the new system. The new system, or rather the old system, but in terms of the, what makes it new is in terms of U and V. What will that be? Well, U prime is x prime plus 2y prime. But I know what x prime and plus 2y prime is because I can calculate it from this. What will it be? X prime plus 2y prime is negative 2x plus twice y prime. So it's plus 2x, that's 0. And how about these two? 2y minus twice this, because I want this plus twice that. So it's 2y minus 2y, again 0. The right-hand side becomes 0 after I calculate x prime plus 2y, so that is 0. That which is, of course, clear. Now, that makes sense, of course, because since the total amount is constant, U prime, that says that U prime is 0. Okay, what's V prime? V prime, well, that's x prime minus y prime. What's that? Well, once again, we have to calculate. It's x prime minus y prime is minus 2x minus x, that's minus 3x. And 2y minus negative y, that makes 3y, plus 3y. All right, what's the system? The system is U prime equals 0, and V prime equals minus 3 times x minus y, but x minus y is V. In other words, these new two variables decouple the system. And we got them, as scientists often do, by physical considerations. These variables go more deeply into what's going on in that system of two tanks than simply the two heights, which are too obvious as variables. All right, what's the solution? Well, the solution is U equals a constant, and V prime, and V is equal to, well, the solution to this equation is some constant, a different arbitrary constant from that one. These are side-by-side equations, which have nothing whatever to do with each other, remember, times e to the minus 3t. Now, there are two options. Either one leaves the solution in terms of those new variables, saying they're more natural to the problem, but sometimes, of course, one wants the answer in terms of the old ones. If you do that, then you have to solve back. In order to save a little time, since this is purely linear algebra, I'm going to write what the, instead of, taking 2 minutes to actually do the calculation in front of you, I'll just write out what the answer is. So to express in terms of U in X and Y, so in other words, this is a perfectly good way to leave the answer if you're allowed to do it. But if somebody says they want the answer in terms of X and Y, well, you have